In this module, we will consider angular momentum. We expect that there should be a rotational counterpart to linear momentum. This angular momentum should be related to torque in the same way that linear momentum is related to force. If we consider the net torque on a point particle at a displacement of r from an axis of rotation, then we find that we can relate that net torque to r cross the time rate of change of the linear momentum. If we bring the r inside the time derivative, then we must subtract off a counter term, dr dt cross p. But dr dt is the velocity, and the velocity is parallel to the momentum, so this term drops out. And we find that we can define an angular momentum, r cross p. And this tells us then that the sum of all the torques acting on a particle is equal to the time rate of change of the angular momentum. While the definition of the angular momentum in terms of r cross p holds for a point particle, we can always construct an extended object in terms of a collection of point particles, and then it still remains true that the sum of the torques acting on an object is equal to the time rate of change of the total angular momentum of that object. For a rotating body with a fixed axis rotation, we also find that we can define the angular momentum in terms of the moment of inertia times the angular velocity. And we can also write that the sum of all the external torques is equal to the moment of inertia times the angular acceleration. However, this last rule only applies in the case where the moment of inertia is constant. Otherwise, we must use the full rule that the sum of the external torques is equal to the time rate of change of the angular momentum. While these equations obviously apply in situations where we have a rigid rotating object, the concepts of angular momentum and torque apply in any situation for any chosen axis of rotation. So consider a point object with mass m moving with constant velocity v in empty space. And let's choose some arbitrary point in space and let that act as the center of rotation. Now we can compute the angular momentum L at the instant when the object has displacement r from this center of rotation. Now, the direction of L fixes the axis of rotation that passes through x. In this case, it's going to be perpendicular to the screen, and we note that the direction of the angular momentum is into the screen by using the right-hand rule, putting our fingers in the direction of r, and then curving them towards the direction of v, which is parallel to the direction of the linear momentum. Then our thumb points into the screen. The magnitude of the angular momentum is going to be the magnitude of this displacement r times the magnitude of the momentum p times the sine of the angle between them. Now, if we consider the full path of this particle in empty space, it's going to follow a straight line, and there's going to be a distance of closest approach d, and we can write the magnitude of the angular momentum in terms of this distance d times the mass times the speed of the object. And we see that both the magnitude and the direction of the angular momentum remain constant for this point particle moving in a straight line in empty space. So even though there is no obvious rotation happening, we can still use the concept of angular momentum, and it is constant here because there are no torques acting on the object. Now we can also consider writing the magnitude of the angular momentum in terms of the tangential component of the velocity. If we do this, then we find that we can write this angular momentum as the moment of inertia times the angular velocity. And then we can express the angular velocity here as v times d divided by r squared. But r is a function of time. And so in this example, while there are no external torques, we clearly see that there is an angular acceleration happening because the angular velocity is a function of time. So how can we have the rule that the sum of all the external torques, which is 0 in this case, is equal to the moment of inertia times the angular acceleration, which is clearly not 0? Well, we have to remember that we mentioned in the previous slide that that relationship between the external torques and the moment of inertia times the angular acceleration assumes that the moment of inertia is constant. And in this case, clearly the moment of inertia is not constant since the radius of the particle is changing in time. Now, in the absence of any external torques, the total angular momentum of a system is conserved. That is, given no net torques, the time rate of change of the angular momentum vanishes. For rotating bodies with a fixed rotation axis, this simplifies to the notion that the final moment of inertia times the final angular velocity is equal to the initial moment of inertia times the initial angular velocity. But in general, what we find is that for an isolated system, both linear momentum and angular momentum are going to be conserved. And furthermore, if there are no inelastic collisions or other internal energy changes, the total mechanical energy will also be conserved. As an example of conservation of angular momentum, let's consider the following. We have a merry-go-round with a moment of inertia I that is initially rotating with an angular speed of omega sub I. A woman of mass m jumps onto the merry-go-round and lands a distance r from the axis of rotation. She does this being sure to jump in the direction directly towards the central axis. What is the final angular speed of the merry-go-round? Well, using conservation of angular momentum, we look at first the initial total angular momentum of the system. This is going to be the moment of inertia of the merry-go-round times its angular velocity omega sub I. And then we also have to add in the angular momentum of the woman as she is jumping, but before she lands on the merry-go-round. She's at some initial radius, r sub I, and she has some initial tangential velocity. But because she jumps directly towards the axis of rotation, and we are considering our rotation axis to be the rotation axis of the merry-go-round, her tangential velocity vanishes, and this term does not contribute. Now, when the woman jumps onto the merry-go-round, the angular velocity of the merry-go-round is going to change. We compute the final angular momentum of the merry-go-round and the woman together. This is going to be the moment of inertia of the merry-go-round times its final angular velocity, plus the angular momentum of the woman as she rotates around with the merry-go-round. This is going to be her moment of inertia, which is m times capital R squared, R being her distance from the axis of rotation. And she will also be rotating with the same angular speed. And so equating the initial and the final angular momenta, we find that the final angular velocity can be written in terms of I times the initial angular velocity divided by I plus mr squared.